Welcome to EPG Pathshala in Computer Science. This is a series of lectures on computer networks. So, we have been looking at some protocols which are useful for multimedia applications. So, we had looked at network layer protocols, we looked at quality of service, then we started looking at multimedia applications and their characteristics and what is it that they typically demand from the network. So, what kind of support would be useful for these multimedia applications from the network. To aid that, we had looked at a couple of applications, typically what is required for streaming media content, either audio or video, and for interactive applications. So, based on that input that we had, we will now be looking at some of the protocols that have been designed to support these kind of applications. So, today we will be looking at the RTP protocol, which is the real-time transport protocol. So, we will look at the design philosophy, we will look at packet formats and other details of this particular protocol. So, we said that there are a number of real-time protocols that have been developed in order to support real-time applications, multimedia kind of applications. So, we have applications which are used for stream description, you have protocols like SDP, SMIL and so on. And then we have stream control protocols which are used to kind of remote control a session, a streaming session, RTSP protocol. Then we have session handling protocols like SIP, SAP, SDP and so on. Then we have the media transport protocols, RTP and RTCP. Okay, this is a pair of protocols that are normally used together. RTP provides the data transport and RTCP is the associated control protocol. So, this is used to send data and metadata. So, we will be looking at some of these protocols. We will start with the transport related protocols, which is RTP and RTCP today. So, if you look at the protocol stack, so far we have looked at the protocol stack with respect to general class of applications. So, where we normally talk about TCP and UDP running over IP, running over some layer 2 protocols. So, now in order to support the multimedia kind of applications, there are few other protocols that have been developed. Okay. So, some of these come under the category of signaling protocols, that is you have H.323, SIP, these session initiation protocol and so on, which are used to signal some information between the client and the server. Then you have streaming protocol, RTSP protocol, and then we have RSVP, we have already looked at RSVP, the reservation protocol, which is used to provide quality of service. Now, RSVP may run either on top of UDP or it may run directly on top of the IP protocol itself. In addition to that, for media transport, we have the media transport protocol, which is RTP. Now, RTP typically is to be used along with other media encapsulation protocols, such as H.261 or MPEG-3 or whatever standards. So, these application level codecs or whatever will work using RTP, which will run on top of UDP and will be carried as IP packets. So, in addition to RTP, we have again RTCP, which aids in providing a quality of service. It is not a quality of service related protocol, but it kind of carries information which may be used by the applications to improve or to adjust the quality of service. So, it is this pair RTP and RTCP that we will be looking at first. We look at RTP now, we may look at RTCP in a subsequent session. So, moving on, the normal question that comes up is why these additional protocols? After all, we had TCP and UDP, why could we not just do with TCP and UDP itself? Why not TCP? So, we have already seen this. TCP, whenever there is a loss, there is a retransmission mechanism, and because of retransmissions there will be a delay, and delays are not as acceptable for us when we talk of real-time applications. And there is a continuous rate fluctuation, which also is not very comfortable for multimedia applications. And why not UDP? After all, it does not have these problems, it is too simple, and typically when you have a firewall or when you have a NAT for instance, UDP packets may be dropped for security reasons. So, UDP is also not really suitable. So, what do we do? So, we try to come up with something in additional, but which make use of this UDP and TCP/SD, because these are two mature protocols which are there which are time tested, which have been running very successfully in the internet. So, we want to make use of these protocols, but do something over and above this, or make use of these for certain purposes. Okay, so, what is it that we make use of them for? UDP is normally used to carry pure audio streaming. So, like for instance in audio and voice over IP kind of applications, and this along with this UDP we can make use of RTP and other protocols which will take care of the requirements for a multimedia application as such. TCP can be used for streaming whenever you have for instance a large buffer which can accommodate delays, which can kind of compensate for delays. So even though you have large delays in TCP, by having large buffers you can compensate for it. So for applications like one-way applications, for example watching clips, video clips on YouTube, you may not mind waiting for a few seconds before the video starts. So in those kind of applications we can do with TCP. But it's definitely not okay for interactive applications like video conference. So we definitely need something more. Okay, so which is where we are moving towards these protocols like RTP and RTCP. So what is this RTP protocol? It's a real-time transport protocol meant for transporting real-time data. So you can say it's a framing protocol for real-time applications, and definitely it's not defining any QoS mechanism for real-time delivery. So please do not confuse RTP as a QoS protocol. It's basically a framing protocol for real-time applications. And RTCP, it's a companion protocol to RTP, and you can say it's a companion control protocol. It's used for carrying control information related to the RTP protocol. So again, this does not guarantee anything, it just provides feedback, provides reports. So using this report, the application will have to take necessary steps. So RTP and RTCP are protocols which aid the application to know something about the network and accordingly adapt its behavior. Okay, so that's the purpose of RTP and RTCP. Now we will look at RTP in detail. Okay. So if you take a look at this pair of protocols, RTP and RTCP, what has been the goal or the philosophy behind the design of these protocols? One of the first things that was definitely kept in mind was that it has to be flexible. That is, you want to provide mechanisms so that you can kind of cater to many different type of applications, but you do not want to dictate any algorithms. Okay, that is, so you should be able to instantiate H.261, MPEG-1, 2, whatever comes, you must be able to kind of handle this without any change to the basic protocol as such. And it should be protocol neutral in the sense that you should be able to work either with UDP IP protocol, the lower layer protocols. You must be able to work with UDP and IP, or it may also be some private ATM networks and so on that you want to work with. Of course, now predominantly it's UDP IP, but whatever other protocol comes in future, that also we should be able to handle. Third is it should be scalable, okay, and it should be able to handle unicast as well as multicast, because remember that when we talk about many multimedia applications, we typically go into conferencing kind of applications, audio conferencing, video conferencing and so on. So where definitely there is a need for multicasting support. So we have many users or many receivers who will have to receive a single piece of multimedia data. And normally what we also try to do is you try to separate the control and the data, okay, so that some functions, the control functions can be taken care of by different protocols if necessary. Okay, so kind of separate control and data, that always gives us a little more control over how the entire process actually can take place. Okay, so now coming to the requirements as such of the RTP protocol. Okay, what is it that we wanted to do? So if we identify the requirements, then we can see if all these things, all these requirements are met by means of whatever information is carried as part of the protocol format and so on. So one of the first things of course is that we need to take care of both types of applications, interactive multimedia applications as well as streaming applications. Now interactive multimedia applications we have seen have strict real-time constraints, streaming applications are not so strict. So whether it is strict real-time constraint or not so strict, both these must be handled by the RTP protocol. Okay, so we need to have a mechanism which is kind of flexible to handle both. Okay. And of course, one of the major goals is that it should allow similar applications to talk to each other. That is, they should be able to negotiate on coding schemes if necessary. They are similar applications, but you may have one application which is connected to a low bandwidth network, another to a high bandwidth network. So in which case, they should be able to negotiate certain parameters, negotiate coding schemes and so on, so that they will still be able to run the application and communicate with one another. So the protocol must have the flexibility to support this kind of negotiation. Third point is that it should help recipients determine the timing relations among data. Now when you talk of real time, obviously we are very much worried about the timing relationship between successive data that is received. So which means we will need some kind of time stamping, some mechanism for synchronization of data, especially when you have multiple media that is being transferred. When you have audio and video being transferred, you need to do things like synchronization. Lip synchronization for instance is very important. If you do not have lip synchronization, when you view for instance a program where lip synchronization is missing, you will see that you hear something but you see something else. It is not a very nice experience as such, viewing experience for the user. So definitely some kind of synchronization will be required. So, we need to have mechanisms to support synchronization. Okay. Further, we know that there will be packet losses, and since it is running, we said that RTP would run on top of UDP, and UDP will not take care of any packet losses as such. So, the application will need to handle the packet loss. So, if the application has to handle packet loss, we need some kind of indications to be given to the application that a packet has been lost. So, you must have some mechanism by which the application is able to identify that a loss has happened. Okay, that is one thing. Second thing is, you must provide some indication of frame boundaries. Now, the reason we talk about frame boundaries is that depending on the application, different applications have different kinds of boundaries. Okay, for instance, when we talk of audio, we talk about talk spurts. That is, there is time when there is a continuous speech that is happening, and then there may be some silent periods. So, you know that when you are transmitting data, you have to indicate that this is the beginning of a talk spurt or it is an end of a talk spurt and so on. Similarly, when looking at video data, for instance, you may be sending different types of frames. We talk about I frame, P frame, B frame and so on. So, there are different requirements of frame boundaries when we talk about different applications. So, we must be able to support these different frame boundaries as well. And you must be able to provide a generic identity for senders independent of the IP address, because we are talking about something which is happening above the IP layer, right. So, we want to have a generic identity for senders independent of IP address, using which you will be able to identify who the source is, who the recipient is and so on. Okay. And all of this we want to do without too much header overhead. So, you want to keep the entire header very simple so that the processing can be done really fast. We do not want to have too much of an overhead. And remember, many of the packets that you may be sending, for instance, when you are sending audio, interactive audio for instance, the packets may be very, very small. The data that is carried in the packets may be very small, in which case if you have too much of header, the header overhead will become too high. So, you will not be using your bandwidth effectively. So, all these are the requirements that we would like to meet using our RTP protocol when you design the RTP protocol. So, let us look at how these requirements are met. Okay. There are two key ideas that are used in the design of RTP protocol. Okay. So, first one is called as application level framing. So, what this means is that you are leaving everything to the, you kind of let the application figure out how it wants to frame the data, how is it that it wants to format the data and so on. So, the idea we are using is that the application knows best as to what it needs. So, let it decide for itself. So, which means different applications can have different profiles, different formats. So, your protocol must be such that it can accommodate different profiles and formats depending on the application. So, the application, on the basis of the application, you will be able to choose different profiles and formats. So, the advantage basically is that you get application specific flexibility. Okay. Second idea that is used is what is called as the end-to-end principle. So, what this means again is that the end systems will take responsibility for providing service irrespective of the network capabilities. Okay. This particular end-to-end principle you can see is in tune with the internet principle, where we say that your network can be simple or dumb and all intelligence is in the at the end system. So, similarly here we are saying intelligence will be at applications, and RTP, the protocol that you have, will just provide a transport service. Okay. And enough of information will be carried in the transport service so that the end machines can figure out what needs to be done. So, with these two key ideas, the entire protocol has been designed. Okay. So, if you look at the features of RTP protocol, you will see that basically it is specified initially in RFC 3550. So, as I said, RTP runs an end system. If you have the end-to-end principle, so it runs on the end systems. So, no RTP running anywhere in the network, meaning at the routers or whatever. Okay. And RTP packets are encapsulated in UDP segments. That is another decision that is taken. And RTP will manage delivery of real-time data. That is, it specifies the packet structure which is required for carrying audio, video data and so on. So, that there is some mechanism to specify that. Okay. And it will provide for interoperability, which means if two VoIP applications run RTP, they can work together, they can talk to each other. Okay. All right. Now, in order to do all these things, what are the other features that are inbuilt or built into RTP? So, RTP packet, if you take a look at it, you will see that it provides some kind of a payload type identification. Now, why do I need a payload type identification? To identify what kind of data is actually being carried, whether it is audio, video, what type of audio, video I am carrying and so on. Okay. So, there is a payload type identification that is specified. There is a source identifier. Remember, we said we wanted to identify who the source is. So, there is a source identifier, and we said there could be loss. So, in order to detect losses, we have a sequence numbering mechanism. Sequence numbers are used so that if something is lost, by looking at the sequence number, you will be able to identify that something has been lost. So, then we said timing recovery is important. So, a time stamping mechanism is used. So, all RTP packets will have a timestamp. Okay. And there are markers for significant events in the data stream. So, we said that we want to have different frame boundaries and so on. So, if I want to mark something, there are markers that are provided, and again these markers can be defined based on the application. So, you get application specific marking or application specific frame boundaries can be specified. Okay. So, the functions, if you look at as such, you can see that you have data functions which basically talk about labeling the content. So, you have source identification, you have loss detection, and you have resequencing. And then you have timing related information. So, with the timing related information that is available, you can do intra-media synchronization, that is within a media stream. You could have, for instance, problems like jitter that occur, right. Jitter, remember, is variation in delay. So, because of variation in delay, you will get a very unstable kind of a picture, or you will not hear the audio properly. So, we know that with playout buffers, by delaying the playout point, you can take care of these things. But to do this, I need to get some idea about the jitter. So, you must be able to calculate jitter, you must be able to identify what is happening. In order to do those kind of functions, RTP will provide some support. So, by means of the timing data that it carries. Okay. Then we can also do intermedia synchronization. So, what we mean by intermedia synchronization is that, for instance, when you have two different medias, that is audio and video, that is being carried together for coming from a single source, you may want to provide some kind of a lip synchronization between audio and video. So, those kind of things also RTP will allow you to do. Okay. Okay. And as we said, RTP runs on top of UDP. So, you have your application layer here, IP layer here, UDP will be on top of IP, and RTP sits above UDP and below the application. So, you can say that with RTP, right, the transport layer is kind of extended. You have UDP plus RTP providing the transport layer functions for the real time applications. Okay. So, in that sense, so this combination of RTP plus UDP together, okay, it will provide you port numbers and IP addresses using which you can uniquely identify the application. It gives you payload type identification, it gives you packet sequence numbering, it gives you time stamping. Okay. All these become possible with the help of this combination. Okay. Now, there is no fixed UDP port that is used for RTP, it is normally negotiated out of band. Okay. And since we have a companion protocol that is used with RTP, the RTCP protocol, the UDP port used for RTCP is normally whichever port is used for RTP, that number plus 1. So, if you are using 5000 for RTP, 5001 will be used for RTCP. Okay. And RTP has this constraint that usually only one media is sent per RTP session, that is per port pair, that is for an RTP RTCP combination, one media will be sent. So, this is the idea that is basically used in RTP. Okay. So, now if you look at the header format, now if you look at the header format, a lot of things become a lot more clearer. So, if you look at the header format, you will see there is first a version field, and then you have a P field which is called as a padding bit, okay, and then you have many other fields here. You have an X field which indicates some extension headers, then there is a CC which indicates contributing sources, account of contributing sources, okay. Then you have an M field which is a marker bit, then you have a payload type field, then we have sequence numbers. You can see there is a timestamp, and you can see that there is a synchronization source ID SSRC, which is basically the source ID that we talked about. So, you can see we have a sequence number, we have timestamp, we have source ID, okay. And you have what is called as contributing source ID. So, if you have more than one source and whose data is all being combined together, that information is also embedded over here. And then there is a provision for extension headers that can be added to it. So, this extension header will normally be added based on applications requirements and so on. Then you have the actual RTP payload header and the payload. So, depending on which payload, what kind of payload type you have, you will have a header here and the actual payload data following that. Okay. So, of this, these first three, okay, are the ones which are, so you can look at each of this is 4 bytes. So, 4 into 3, 12 bytes forms the standard part of RTP header. The rest of the things are added depending on the situation, depending on the application. So, just looking at each of these bits now. So, version, it is a version identifier. This P is a padding bit. Now, padding bit is used whenever the RTP payload is padded, because we want everything to be, the entire packet to be in multiples of 4 bytes. So, what happens here is that when padding is used, the last byte of the padding, that gives the number of bytes that are padded. So, using that you can count back and look at which are the extra bytes that have been added, and you can remove them. Okay. And there is an X bit, this basically is set whenever there is an extension header added, as we said. CC refers to the count of contributing sources. M is a marker bit which is used for identification. PT is payload bit. Sequence number is a number which is used to detect missing and misordered packets. Now, this M and PT are both defined by the application profile. So, you have what are called as different application profiles which are used, and they specify what the format of M and PT should be and what should be there in that particular payload header and so on. So, the payload type, as we said, okay, it indicates the type of encoding that is currently being used is 7 bits. So, if the sender changes the encoding during the call, then the sender informs the receiver through this payload type field. So, which means even during the call, if there is a drop in the bandwidth, you can accommodate for those changes. So, you have different payload types, right? 0 indicates PCM mu law, 3 is GSM 13 kilobit per second. You can see the different data rates are supported using the different payload types that you have. Okay. And the sequence number field that we looked at, that is a 16-bit sequence number field. So, it is incremented by 1 for each RTP packet that is sent. So, you can use this to detect packet loss and restore any packet sequences. Okay, so that was the first line of the header. Now, the second line, that is where we have the timestamp. So, if you look at how the timestamp is handled, this is used to enable as we said, different multimedia streams to be synchronized. So, what this actually consists of is actually it's a counter, okay, of ticks. Now, this what exactly is a tick would depend on the application. So, the granularity of the ticks as such can be defined by the application. It's an application specific timestamp that you are actually determining. Okay. So, and the timestamp in a particular packet will refer to the time at which the first sample in that packet was generated. Okay. And difference in timestamps can be used for synchronization purposes. Okay. That is the purpose of the timestamp field. Then you have a synchronization source ID. This uniquely identifies the single source of the RTP stream. And contributing source ID is when there are a number of RTP streams, for instance, which pass through a mixer. The mixer will become the SSRC, the synchronization source, and the other contributing sources, their IDs will be mentioned over here. So, this is basically what you will have. So, coming back to the timestamp field, okay, that is a very important field because we need to clearly understand how that is used. Okay. So, if you look at the timestamp field, 32 bits long, and as I said, it gives you the sampling instant of the first byte in that RTP data packet, first byte or first sample in that RTP data packet. So, if you take audio for example, now audio, let us say I am sampling at using an 8 kilohertz sampling clock, which means you have about every 125 microseconds a sample is being taken. So, the timestamp clock will increment by 1 for each sampling period. That is, once every 125 microseconds the timestamp clock will be incremented. Okay. So, if the application is generating chunks of 160 encoded samples, for instance, for 20 milliseconds of samples are being sent as one chunk. Okay. So, in 20 milliseconds, what would I get? I would get 160 encoded samples. So, which means the timestamp in subsequent packets will be incremented by 160, because in the previous thing I would have had, if I had a timestamp of X, the next RTP packet is going to have the 161st sample, right, starting from the first one. So, it will have the value of X plus 160. So, that will be the value which you will find in the timestamp field. So, it kind of tells you exactly what is the timing relationship between these two packets. Okay. The sequence number field, however, will be incremented only by 1. So, by looking at the sequence number field, which tells you this packet follows this packet, and by looking at the timestamp information, you will know exactly how many samples are being carried, and then you will be able to find out what is the timing relation that you have between these two packets, and then you will be able to play it back at the appropriate rate. Okay. So, timestamp clock will continue to be increased at the constant rate even when the source is inactive. For instance, we talked about having silent periods, right. So, if you have talk spurts and you have a silent period, even during the silent period you may not be transmitting the data, but you are sampling the data as such, right. So, but the value is 0, so you are not transmitting it, but the timestamp will continue to be incremented. So, that is how you will be able to also replay the silent periods also on the other end. Okay. That is the beauty of how this timestamp field is used. And the source SSRC field that we talked about, that is a 32-bit long field. It is used to identify the source of the RTP stream, and each stream in the RTP session will have a distinct SSRC. Okay. So, this is just a small example to understand this. So, let us say we are sending the same example of 64 kilobit per second PCM encoded voice over RTP. So, the application will collect the encoded data in chunks, for example, every 20 milliseconds. So, you will have 160 bytes in a chunk. Okay. So, now the audio chunk, so we are assuming that you are sending 1 byte per sample. Okay, 160 samples are there, 1 byte per sample. So, you will have 160 bytes in the chunk. So, this 160 byte chunk plus the RTP header, that forms the RTP packet, okay, which will now be encapsulated in a UDP segment and it will be sent. Okay. Now, the RTP header will indicate the type of audio coding that is used in the packet, okay, so, and obviously sender can also change the encoding during the conference if I have a conference that is going on. Okay. And the RTP header will also contain sequence numbers and timestamps. So, using this the receiver will be able to replay the data. Okay. This is overall flow of how things happen. Okay. Now, in addition to this, there are a few other interesting things that one can do with RTP. Okay. So, for instance, you could use multiplexing of different sessions and you could use SSRC as the multiplexing ID to separate them out. Okay. For instance, let us say we have a situation like this. I have an office at this end of a telephone network and at this end of a telephone network, right, or two offices at two different locations, let us say. This is connected, which are connected by means of a voice over IP network. Okay. So, you have a IP network through which using a voice over IP gateway, you want to transfer data from an office which is here to an office which is there. Okay. So, now what happens? This may be connected to a public telephone network, here also it is connected to a public telephone network. There is a voice over IP gateway on either side, okay, and then there is a IP cloud here. So, this is your IP network. Okay. Now, let us assume that these are branch offices. So, at the branch offices, you may have many phone calls between these two branch offices. So, what we do is each of them, right, will be carried using different SSRC IDs within the same RTP session, for instance. So, but by using the different SSRC IDs, the source synchronization source IDs, at the gateway here, you will be able to separate them out and send them on to the different receivers or different, you can identify that they are different streams. So, you can send it to the corresponding users on either side. Okay. So, this multiplexing using SSRC becomes a very efficient way of combining many voice over IP packets or many sessions of RTP and sending it as a single session. Okay. So, this is one thing that is done. Okay. So, you only have one RTP session between the voice over IP gateways. Okay. It's not, so though you have multiple calls that need to be handled, with a single session of RTP you are able to send the data. Okay. This is one example of how RTP is used. Okay. Similarly, you have other devices which are called as RTP mixers. So, these are normally used when you want to combine the streams from different sources. Okay. You have different source. So, I have different SSRCs 1, 2, 3 and so on. So, for instance, this may be on a high bandwidth network, connected on a high bandwidth network. The receiver may be connected to a low bandwidth network. So, in which case this device called a mixer which comes in between, okay, can now combine the data coming from these and then play it out at a rate which can be handled by the receiver. So, in which case this mixer will become the SSRC and your SSRC 1, 2 and 3 will now become the contributing sources. So, we talked about CSRCs, right. So, in this kind of situation when data is sent from the mixer to the receiver, an RTP session will be established here and for this session you will find that these SSRCs become the CSRCs and the mixer will become the SSRC which is actually handling this session. Okay. So, like this there are many uses of the RTP protocol and many uses of how you can use this information that is carried in the RTP protocol to distinguish between sessions, to carry data appropriately and so on. Okay. Of course, along with the RTP protocol we also have the RTCP protocol. So, it is this combination that gives a lot of strength to the multimedia session management or the transport management that we are talking about. Okay. We will look at RTCP later, but with this idea of RTP you should be able to figure out how the protocol is designed, right, in such a manner that whatever features are required are kind of provided. Okay. Now, when you talk of RTP packets, if you see there are some interesting facts about this packet format as such. You will see that there is no protocol field. So, how do I identify what is the protocol? Okay. So, what you will actually have to do is you will have to check for the version field or you will have to check for some fields in the stream of packets. So, you will have to maybe you will have to do something like a per flow checking, that is look for a constant SSRC and increasing sequence numbers to identify a flow and use that to validate whether it is a proper RTP packet and so on. Okay. So, to summarize what we have looked at in this session, we have started with the design goals of RTP, okay, and then we looked at the fundamental principles of design of RTP, then we looked at the protocol, the message format, and we saw how the different fields help in carrying the RTP sessions, and we also saw some brief uses of this RTP protocol for carrying various sessions. Okay. So, we will be looking at RTCP later. So, this is a quick introduction to RTP. Thank you.